There are questions that haunt the edges of human understanding, questions so vast, so fundamental, that they've echoed through millennia of philosophical inquiry. What is existence? What lies beyond the veil of the known? Are we alone in this cosmic theatre, or are there other actors performing in distant wings, under different lights, governed by rules we cannot yet comprehend? These questions once belonged solely to the realm of philosophy and religion, debated in candlelit chambers and contemplated beneath star-filled skies. But something has changed. We now possess instruments capable of peering into the deepest recesses of space and time, machines that can capture photons that have travelled for billions of years, carrying messages from the universe's infancy. And what these instruments are, revealing challenges not just our scientific models, but our very conception of what reality can be. The James Webb Space Telescope represents humanity's most ambitious attempt to answer these ancient questions through empirical observation. Positioned nearly 1 million miles from Earth, hovering at a gravitationally stable point known as Lagrange Point 2, this marvel of engineering operates in the profound cold of space, its instruments cooled to temperatures barely above absolute zero. Its primary mirror, composed of 18 hexagonal segments coated in gold, spans more than 21 feet across a golden eye, gazing into the cosmic abyss. Unlike its predecessor, the Hubble Space Telescope, which primarily observed visible light, Webb sees the universe in infrared wavelengths, allowing it to pierce through cosmic dust and peer across unimaginable distances to epochs when the first stars ignited in the primordial darkness. Since becoming operational, Webb has fundamentally altered our understanding of cosmic history. It has revealed galaxies that formed mere hundreds of millions of years after the Big Bang, impossibly massive, impossibly organized structures that shouldn't exist according to our carefully constructed models of cosmic evolution. It has analyzed the atmospheres of exoplanets orbiting distant suns, detecting chemical signatures that hint at conditions we never imagined possible. It has captured images of stellar nurseries where new suns are being born, and documented the violent deaths of massive stars in their final moments. Each discovery has been remarkable. Each observation has expanded the boundaries of known science. But what Webb has recently detected defies categorization. It challenges our fundamental assumptions about the nature of space, time, and matter itself. The discovery centers on an object, though calling it an object feels inadequate, perhaps even misleading, located in a region of space that should, by all conventional understanding, be unremarkable. No massive galaxy clusters nearby, no obvious sources of extreme gravitational distortion, no violent cosmic events occurring in its vicinity. Just a patch of seemingly empty space that, upon closer examination, revealed something that has left astronomers struggling for explanations. The initial detection came through routine observations, part of Webb's systematic survey of deep space. A subtle anomaly in the infrared signature, a pattern of light that didn't conform to any known phenomenon. At first, researchers assumed instrumental error, perhaps a calibration issue, or interference from some mundane source. But as additional observations accumulated, as the data was analysed and reanalyzed, as alternative explanations were systematically eliminated, a disturbing realization began to crystallize. They were observing something genuinely unprecedented. What makes this discovery so profoundly unsettling isn't merely that it's new or unexpected. Science thrives on the unexpected. Anomalies drive progress and expand understanding. What disturbs researchers is the fundamental nature of what they're observing. A phenomenon that appears to violate principles we considered sacrosanct, that suggests our current framework for understanding reality may be incomplete in ways we hadn't imagined. The object, for lack of a better term, exhibits properties that seem mutually exclusive. It appears to exist simultaneously in multiple states, to occupy positions in space that cannot be reconciled with our understanding of geometry, to emit radiation patterns that defy the laws of thermodynamics as we understand them. To grasp the significance of this discovery, we must first understand the cosmological framework against which it appears so anomalous. Our current model of the universe, refined through a century of observations and theoretical work, describes a cosmos born approximately 13.8 billion years ago in an event we call the Big Bang. In the initial moments, all of space existed in an unimaginably hot, dense state. As the universe expanded and cooled, fundamental forces separated from their unified origin. Quarks combined to form protons and neutrons. After roughly 380,000 years, the universe had cooled sufficiently for electrons to bind with atomic nuclei, forming the first neutral atoms, primarily hydrogen and helium. This moment, known as recombination, marked a profound transition. Before recombination, the universe was opaque, a roiling plasma through which light could not travel freely. After recombination, photons could traverse space unimpeded, and the universe became transparent. Those first photons, released at the moment of recombination, still permeate the universe today as the cosmic microwave background radiation, a faint glow detectable in every direction, the cooling remnant of the universe's fiery birth. For hundreds of millions of years following recombination, the universe existed in what cosmologists call the cosmic dark ages, a period when no stars yet burned, no galaxies yet shone, when the cosmos consisted of vast clouds of hydrogen and helium drifting through expanding space. Gradually, gravity began its patient work, drawing matter together into ever denser concentrations. Where the primordial density was slightly higher by mere fractions of a percent, matter accumulated more rapidly. These overdense regions grew through gravitational attraction, eventually collapsing into the first stars. These primordial suns were nothing like the stars we observe in our modern universe. Formed purely from hydrogen and helium, lacking the heavier elements that would later seed from stellar deaths, they could grow to enormous masses, perhaps 100 times, even 200 times, the mass of our Sunday. These cosmic behemoths burned ferociously hot and died quickly, sometimes in less than a few million years. Their deaths were cataclysmic, explosive supernovae that scattered the first heavy elements into space, seeding the cosmos with carbon, oxygen, silicon, iron, the building blocks of planets, and, eventually, of life itself. The first stars congregated into the first galaxies, which began as small, irregular collections of stars that gradually merged and evolved through cosmic time. Our models predicted this galaxy formation should be a slow, hierarchical process, with small galaxies forming first and then combining over billions of years into larger structures. The massive elliptical galaxies and grand spirals we observe in the nearby universe should represent the culmination of this long, evolutionary process, requiring billions of years to assemble their enormous masses and develop their complex structures. This is where Webb's observations have proven deeply challenging to conventional wisdom. The telescope has detected massive, seemingly mature galaxies, existing when the universe was only a few 100 million years old, a cosmic eye blink after the Big Bang. These galaxies possess masses and structural complexity that our models suggest should require several billion years to develop. It's as if we discovered a fully grown oak tree in a forest that was planted last week, possible, perhaps, under conditions we don't yet understand, but profoundly at odds with our expectations based on current theory. The implications are significant. Either our models of galaxy formation are fundamentally flawed, missing some crucial physical process that allows galaxies to form far more rapidly than we believed possible, or our understanding of the early universe's conditions is incomplete. Perhaps the dark matter, that mysterious substance that comprises roughly 85% of all matter in the universe, but interacts with ordinary matter only through gravity, behaved differently in the early cosmos than it does today. Perhaps the initial density fluctuations in the primordial universe were larger than our models predict, allowing matter to collapse into gravitationally bound structures more quickly. Perhaps some exotic physical process, unknown to current science, accelerated early galaxy formation. These discoveries, profound as they are, represent puzzles within the existing framework of cosmology. They challenge specific aspects of our models while remaining, at least potentially, explicable through modifications to known physics. The anomaly Webb has recently detected is different. It doesn't just challenge a specific model or theory. It appears to challenge fundamental principles, the bedrock assumptions upon which our entire understanding of physical reality rests. The anomalous object occupies a region of space approximately 13 billion light-years from Earth. Light from this location has travelled for 13 billion years to reach Webb's detectors, meaning we're observing this region as it appeared roughly 800 million years after the Big Bang, relatively early in cosmic history, but well past the initial moments of creation. At this epoch, the first galaxies were forming, the first stars were illuminating the darkness, the universe was transitioning from its primordial simplicity to the complex tapestry of structure we observe today. Nothing about this epoch should produce what Webb has detected. The first anomaly lies in the object's spectrum, the breakdown of its light into component wavelengths, a technique that reveals the composition and physical state of distant objects. When astronomers first analysed the spectrum, they found absorption and emission lines that don't correspond to any known element or molecular structure. Every element produces a unique spectral fingerprint, a characteristic pattern of dark absorption lines and bright emission lines at specific wavelengths, determined by the element's electron configuration. These spectral signatures are as distinctive and reliable as human fingerprints. We can identify elements across billions of light years with absolute confidence because the fundamental physics governing atomic structure doesn't change across space or time. Or so we believed. The spectral lines detected from this object occur at wavelengths that don't match any element on the periodic table, nor any plausible molecular combination. They don't correspond to known ionization states of familiar elements. They can't be explained as redshifted versions of familiar spectral signatures. The pattern itself is orderly, suggesting some underlying structure. But the structure doesn't conform to the quantum mechanical principles that govern atomic physics as we understand it. It's as if the light is being absorbed and emitted by matter, operating under different rules, following a different quantum logic than the atoms and molecules that comprise everything we've ever studied. Several possible explanations were immediately proposed. Perhaps these are signatures of exotic matter states, achievable only under the extreme conditions of the early universe. Temperatures, pressures, or densities we've never replicated in laboratories or observed elsewhere in the cosmos. Perhaps they represent complex molecules of a type we've never encountered, organic chemistry of such complexity that its spectral signature appears alien. Perhaps intense magnetic fields are splitting energy levels in ways that produce these unusual spectral patterns, a phenomenon called the Zeeman effect, but operating at extremes beyond our experience. But as researchers explored these possibilities, each explanation encountered insurmountable difficulties. The temperatures and pressures required to produce these spectral signatures through exotic matter states would also produce other observable effects, X-ray emissions, particular patterns of radio waves, characteristic signatures of high-energy physics, none of which are detected. The molecular explanation fails because no plausible molecular bonding scheme can produce the observed pattern. The spectral lines don't split or shift in ways consistent with magnetic field effects. One by one, conventional explanations were examined and discarded. The second anomaly is even more perplexing. The object's luminosity, its total energy output across all wavelengths, fluctuates in ways that violate energy conservation principles. Specifically, the object brightens and dims with a precise periodicity of approximately 3.7 hours, but the total energy emitted during bright phases substantially exceeds the energy emitted during dim phases by a factor that cannot be accounted for by any internal energy reservoir. It's as if the object is somehow borrowing energy from nowhere, radiating more than it should be capable of producing, then returning to a lower energy state without expelling that excess energy in any detectable form. Energy conservation is perhaps the most fundamental principle in physics. It states that energy cannot be created or destroyed, only transformed from one form to another. This principle has been tested in countless experiments across every domain of physics, from quantum mechanics to cosmology, and has never been observed to fail. It's built into the very structure of our physical theories, emerging from deep symmetries in the laws of nature. If energy conservation is violated, then the mathematical frameworks we use to describe reality are fundamentally flawed at a level so basic that it calls everything into question. Researchers have desperately sought explanations that preserve energy conservation. Perhaps the object is accreting matter during dim phases and converting that matter into energy during bright phases, but there's no evidence of surrounding material being drawn inward, no accretion disk, no surrounding gas clouds being depleted. Perhaps it's extracting rotational energy from a spinning core, but the periodicity is too stable, showing no signs of the gradual slowdown that would accompany rotational energy loss. Perhaps it's a binary system where one component periodically eclipses the other, creating an illusion of changing total luminosity, but detailed analysis of the light curves shows this can't account for the observations. The third anomaly involves the object's position in space itself. Webb's observations include precise astrometric measurements, the exact angular position of the object on the sky, measured with extraordinary precision. Over the course of several months of observations, researchers noticed something impossible. The object's position shifts in ways that cannot be explained by any known celestial mechanics. It's not moving through space in a simple trajectory. It's not orbiting a more massive companion. The shifts in position don't correspond to gravitational lensing effects, where intervening mass distorts the light path. The object appears to be in multiple locations simultaneously, with the detected position varying between observations in ways that defy the geometry of Euclidean space. This is perhaps the most philosophically troubling aspect of the discovery. Space itself, as we understand it, is the stage upon which physical events occur. Objects occupy positions in space and move through space continuously, following trajectories determined by forces acting upon them. The concept of an object existing in multiple positions simultaneously belongs to quantum mechanics at microscopic scales, where particles can exhibit wave-like properties and exist in superposition states until measured. But this is a macroscopic object, emitting vast amounts of energy, existing at cosmic scales. The quantum superposition interpretation, even if we were willing to entertain it, breaks down at scales far smaller than what we're observing. Some researchers have proposed that what appears as a single object might actually be multiple objects, perhaps a previously unknown class of gravitationally bound system, where several components are so precisely synchronized that they mimic the signature of a single source. But this explanation requires extraordinary fine-tuning, demands that multiple separate objects coordinate their behavior with impossible precision across vast distances, and still doesn't account for the spectral anomalies or the energy conservation violations. Others have suggested we might be witnessing effects of quantum gravity, the still theoretical framework that would unite quantum mechanics and general relativity, describing gravity's behavior at the smallest scales where both quantum effects and gravitational effects become important. Our current theories of gravity, based on Einstein's general relativity, treat space-time as a smooth, continuous fabric. Quantum mechanics suggests that at sufficiently small scales, the Planck length, approximately 10 to the negative 35 meters space-time itself, might be quantized, possessing a grainy, discrete structure rather than smooth continuity. If quantum gravitational effects can somehow manifest at large scales under certain conditions, perhaps they could produce the spatial anomalies being observed. But this explanation, while tantalizing, faces severe difficulties. Quantum gravitational effects are expected to be utterly negligible at scales larger than the Planck scale, relevant only in the most extreme environments like black hole singularities or the first instance of the Big Bang. No known mechanism would amplify these effects to visibility at the cosmic scales we're observing. It would require physics so far beyond our current understanding that we have no framework even to formulate the relevant theories. The astronomical community's response to these observations has been a mixture of intense excitement and profound skepticism. Science thrives on anomalous observations, on data that doesn't fit existing frameworks, because such anomalies drive progress and lead to deeper understanding. But scientists are also necessarily conservative about claims that would overturn fundamental principles. Extraordinary claims require extraordinary evidence, and the more fundamental the principle challenged, the more rigorous the verification demanded. Multiple independent research teams have requested Webb observing time to verify and extend the initial observations. The telescope's schedule is intensely competitive, with far more proposed observations than available time. But the potentially revolutionary nature of this discovery has led to a reallocation of resources. Additional observations have been conducted across different wavelength ranges, using different instrumental configurations to rule out artifacts or systematic errors specific to the initial observation mode. These follow-up observations have, disturbingly, confirmed the original findings. The spectral anomalies persist across all observing modes. The energy fluctuations continue with the same impossible periodicity. The positional ambiguities remain unexplained. If anything, the additional data has deepened the mystery. Higher spectral resolution observations reveal even more anomalous spectral lines, suggesting complexity that earlier, lower resolution data couldn't capture. Extended monitoring of the luminosity variations shows additional subtle patterns within the main 3.7-hour cycle, nested periodicities that hint at some intricate underlying mechanism we cannot begin to model. Theoretical physicists have begun exploring whether modifications to known physics might explain the observations. Some propose that the constants of nature quantities, like the speed of light, the gravitational constant, the charge of the electron, might have been different in the early universe, and that we're observing a region where these constants retained their primordial values, while elsewhere they evolved to the values we measure today. This is an extraordinarily radical proposal. Our entire understanding of physics assumes that fundamental constants are truly constant, unchanging across space and time. If they vary, then the laws of physics themselves are contingent, dependent on local conditions, and the notion of universal physical law becomes questionable. Others have suggested we might be observing effects from extra-spatial dimensions beyond the three we experience directly. String theory and related frameworks propose that reality contains more than the three spatial dimensions of everyday experience, perhaps 6 or 7 additional dimensions, compactified to such small sizes that we don't notice them directly. Under certain exotic conditions, perhaps involving intense gravitational fields or high energy densities, these extra dimensions might become temporarily accessible, allowing energy or information to leak between our familiar three-dimensional space and the hidden dimensional realms. Could the energy conservation violations be explained by energy flowing into or out of extra dimensions? Could the positional anomalies reflect an object partially extending into dimensional spaces we cannot directly observe? These proposals, while creative, remain speculative in the extreme. String theory, despite decades of development, has yet to make specific, testable predictions that would allow verification through observation. The extra-dimensional scenarios require conditions so far beyond our ability to probe experimentally that they effectively remain mathematical possibilities rather than physics in the empirical sense. A more conservative interpretation suggests that what we're observing might be some unprecedented astrophysical phenomenon involving known physics in an extreme configuration we haven't previously encountered. Perhaps a binary system involving exotic stellar remnants, black holes, neutron stars, or even hypothetical objects like quark stars interacting in ways that produce these strange signatures. Perhaps plasma physics in extreme conditions can generate spectral features we've never observed because we've never before seen plasma at precisely these temperatures, densities, and magnetic field strengths. The difficulty with these astrophysical explanations is that while they might potentially account for one or perhaps two of the observed anomalies, no single astrophysical model can explain all of them simultaneously. The spectral anomalies, the energy violations, and the positional ambiguities seem to demand separate, unrelated explanations, and coincidence on this scale strains credibility. When multiple independent anomalies occur in the same object, the natural inference is that they arise from a common underlying cause, some single phenomenon that manifests in these various, observationally distinct ways. What haunts researchers most deeply is the possibility that we're confronting a limitation not of our instruments or our data, but of our conceptual frameworks themselves. Throughout the history of science, there have been moments when accumulated observations simply could not be reconciled with prevailing theories, when the existing paradigm had been stretched to its breaking point. The motion of planets could not be explained within the Ptolemaic geocentric model, no matter how many epicycles were added to the calculations. The nature of light could not be understood within purely wave-based or purely particle-based frameworks, requiring the development of quantum mechanics to resolve. The orbit of Mercury could not be explained by Newtonian gravity, necessitating Einstein's revolutionary reconceptualization of gravity as the curvature of space-time itself. Are we now, at such a juncture? Is Webb's anomalous detection a signal that our current understanding of reality, quantum mechanics, general relativity, the standard model of particle physics? The cosmological standard model represents an approximation to some deeper truth that we have yet to glimpse. The thought is simultaneously terrifying and exhilarating. Terrifying because it suggests that what we confidently consider knowledge might be revealed as incomplete, that the edifice of understanding built over centuries might require fundamental reconstruction. Exhilarating because scientific progress occurs precisely through such revolutions, through the discovery of deeper layers of reality previously hidden from view. The philosophical implications extend beyond physics into questions about the nature of observation and reality itself. Quantum mechanics has already taught us that observation is not a passive recording of pre-existing facts, but an active process that affects what is observed. The famous double-slit experiment demonstrates that particles can behave as waves when unobserved, passing through both slits simultaneously, but collapse into definite particle trajectories when measured. This wave-particle duality, this fundamental indeterminacy in the nature of quantum entities, challenges our intuitive notion that objects possess definite properties independent of observation. But quantum mechanics, strange as it is, operates within a well-defined mathematical framework that makes precise predictions confirmed by countless experiments. What Webb has detected seems to lie beyond even quantum mechanics' strange but rigorous structure. The positional ambiguities aren't explained by quantum superposition. We're not dealing with microscopic particles in controlled laboratory conditions, but macroscopic energy sources across cosmic distances. The spectral anomalies don't fit quantum mechanics predictions for atomic structure. The energy fluctuations violate principles that quantum mechanics respects, even as it introduces fundamental uncertainty into other aspects of physics. Some philosophers of science have suggested that what we're confronting might be a fundamental limitation on knowability itself, an instance where the universe presents us with phenomena that cannot, even in principle, be fully understood within any mathematical framework accessible to human cognition. This is a deeply unsettling possibility. Science has proceeded for centuries on the assumption that nature, however complex, operates according to laws that can ultimately be discovered and expressed in mathematical form. The periodic table, Maxwell's equations of electromagnetism, Einstein's field equations, the Schrödinger equation, these represent humanity's greatest achievements, the capture of natural phenomena in precise mathematical language that allows prediction and understanding. But what if some phenomena lie beyond this approach? What if the universe contains aspects that cannot be compressed into human mathematical frameworks, not because we lack sufficient intelligence or creativity, but because those aspects of reality don't conform to mathematical structure at all? This possibility strikes at the heart of the scientific enterprise, suggesting boundaries to empirical knowledge that cannot be overcome through better instruments or cleverer theories. Yet even this deeply skeptical position might be premature. History counsels humility when declaring phenomena inexplicable. To a physicist of the 19th century, quantum mechanics would have seemed impossible. Its core principles, uncertainty, superposition, entanglement, so contrary to everyday experience and classical physical intuition that they would have been dismissed as incoherent. Yet quantum mechanics not only makes sense, it forms the foundation of modern technology, enabling transistors, lasers, magnetic resonance imaging, atomic clocks, and countless other applications. What seems inexplicable often becomes comprehensible with conceptual advances we cannot anticipate from within our current frameworks. The search for understanding continues with renewed urgency. Researchers are analyzing the Webb data using novel mathematical techniques, applying frameworks from information theory, complex systems science, and topology branches of mathematics that describe structural properties independent of geometric specifics. Some have noticed patterns in the timing of the luminosity variations that suggest strange attractors, mathematical structures characteristic of chaotic but deterministic systems. If the energy fluctuations are indeed chaotic in the technical sense, this might explain why they appear random while exhibiting precise statistical regularities. Others are revisiting archived data from previous telescopes, searching for earlier, possibly overlooked observations of similar phenomena. Perhaps this isn't a unique object, but represents a new class of cosmic entities, rare enough that they've escaped systematic detection, but present in the historical record if one knows what to look for. Initial searches through Hubble data have identified several candidates showing spectral peculiarities reminiscent of Webb's discovery, though none displaying the full suite of anomalous properties. These candidates are now priority targets for Webb follow-up observations. Ground-based observatories have joined the effort, though their capabilities are limited compared to Webb's infrared sensitivity and spatial resolution. Still, they can provide continuous monitoring at visible wavelengths, watching for any variability or transient events that might provide clues to the underlying physics. Radio observatories are searching for signals at longer wavelengths, mapping the region around the anomalous object for any associated structures or energy sources invisible to infrared and optical instruments. Theoretical work has intensified across multiple fronts. Cosmologists are exploring whether the early universe might have produced transient conditions, the brief epochs when the physics was different from what it later became that could generate objects with properties impossible under modern conditions. Perhaps in the first billion years after the Big Bang, before the universe fully settled into its current state, exotic matter states or field configurations existed that have since decayed or transformed. If so, what we're observing might be a fossil of that primordial era, a remnant of physics that no longer operates anywhere in the modern universe. Particle physicists are investigating whether unknown particles or forces beyond those in the Standard Model might be involved. The Standard Model describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, along with the matter particles those forces act upon. It's extraordinarily successful, accurately predicting the results of particle physics experiments to remarkable precision. But we know the Standard Model is incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It contains unexplained parameters whose values must be measured rather than predicted by the theory. Perhaps a more complete theory, incorporating additional particles or forces, would explain Webb's observations. Dark matter itself remains one of physics' deepest mysteries. We know it exists through its gravitational effects. Galaxies rotate too rapidly to be held together by the gravity of their visible matter alone. Galaxy clusters contain far more mass than can be accounted for by stars and gas. The large-scale structure of the universe requires dark matter's gravitational influence to form. Yet we don't know what dark matter is. It doesn't emit or absorb light, doesn't interact through electromagnetic forces, passes through ordinary matter, essentially unimpeded. Decades of experiments have searched for dark matter particles, placing increasingly stringent constraints on their properties. but no confirmed detection has emerged. Could Webb's anomalous object involve dark matter in some unexpected way? Perhaps under certain conditions, dark matter particles can interact with ordinary matter or with each other more strongly than they do in the present-day universe. Perhaps the object is partially composed of dark matter in an exotic state, producing the strange observational signatures through interactions we've never previously witnessed. This would explain why the spectral lines don't match known elements they might represent transitions in dark matter particle states rather than atomic electron transitions. The positional ambiguities might also find explanation through dark matter. If dark matter can form bound structures analogous to how ordinary matter forms stars and planets, perhaps these structures have properties utterly unlike anything in our experience. Maybe they don't occupy single definite positions in the way ordinary matter objects do. Maybe their gravitational influence creates lensing effects that make a single source appear distributed across space. These ideas remain highly speculative, but the nature of this discovery demands speculative thinking. Some researchers have begun considering possibilities even more exotic. Could this be evidence of a white hole, the time-reversed analogue of a black hole, a hypothetical object that expels matter and energy rather than consuming it? White holes are solutions to Einstein's field equations, mathematically valid but never observed, generally considered physically unrealistic because they would require extraordinarily special initial conditions and would be unstable. But perhaps in the early universe, such conditions existed. Perhaps we're witnessing a white hole slowly dissipating, the energy fluctuations representing matter and radiation being expelled from this cosmic spigot. Or could the object be a naked singularity? A singularity like those believed to exist at black hole centers, but not hidden behind an event horizon. General relativity permits such solutions, but the cosmic censorship hypothesis suggests that nature prohibits naked singularities, that all singularities must be clothed in event horizons that hide their most extreme properties from external observation. If naked singularities can exist, they would be regions of infinite spacetime curvature, directly observable, where the equations of general relativity break down completely. The positional ambiguities and energy violations might be symptoms of a naked singularity's pathological properties, manifestations of a point where our physical theories simply fail. Even more speculatively, some have wondered whether this could be evidence of another universe impinging on our own. The multiverse concept, arising from various approaches to cosmology and quantum mechanics, suggests that our universe might be one of many, perhaps infinitely many, existing within a larger reality. In most multiverse scenarios, these separate universes are completely causally disconnected, unable to influence each other. But some theoretical frameworks allow for rare interactions, perhaps through quantum tunneling effects, or through shared higher dimensional spaces. Could we be observing a point where another universe is brushing against ours, where matter or energy, or even the laws of physics themselves, are leaking across the boundary between cosmic domains? These ideas, fascinating as they are, remain firmly in the realm of speculation. They are what physicists explore when confronted with data that defies conventional explanation. A catalogue of exotic possibilities to be investigated, to be subjected to mathematical scrutiny, to be tested against observation where possible. Most of these speculations will prove wrong. Science advances not just through creative hypothesis, but through rigorous testing, through the elimination of ideas that don't withstand empirical challenge. What makes this discovery particularly significant is that it exists at the intersection of multiple research frontiers. It touches on cosmology and the nature of the early universe. It involves questions about fundamental constants and whether physical laws are truly universal. It potentially engages quantum mechanics, general relativity, and the search for a unified theory combining them. It might implicate dark matter, the mysterious substance that dominates the universe's mass budget. It challenges our understanding of space, time, and causality themselves. In this way, the anomaly represents a perfect storm of deep questions, a phenomenon that could potentially illuminate multiple mysteries simultaneously if we can unravel its nature. Or it might prove to be a complex but ultimately explicable astrophysical phenomenon, unusual but understandable within known physics once all the relevant conditions are properly identified and analysed. The only certainty is that we don't yet know. The broader implications for cosmology are profound regardless of the specific explanation that eventually emerges. If the early universe could produce objects or conditions so radically different from anything in the modern cosmos, then our observational sample of cosmic history is far more incomplete than we realized. We've been conducting deep surveys of the distant universe for decades, building up a census of galaxies and quasars across cosmic time, tracing the evolution of structure from the primordial density fluctuations to the rich cosmic web of today. But if rare, exotic phenomena existed in the early universe and have largely escaped detection because we didn't know to look for them or couldn't recognize them when we saw them, then our picture of cosmic history has significant gaps. This possibility has led to a re-evaluation of earlier observations. Teams are combing through archival data from Hubble, Spitzer, and other telescopes, applying new analysis techniques designed to identify spectral or variability signatures similar to what Webb detected. They're examining objects previously catalogued as unusual but not anomalous enough to warrant extensive follow-up, wondering whether some were dismissed too quickly, whether patterns visible in hindsight were overlooked because they didn't fit expected categories. Several potential analogues have been identified, objects showing one or two of the anomalous properties, though none displaying the complete syndrome of weirdness that characterizes Webb's primary detection. These objects are now targets for intensive study. If a pattern emerges, if these objects share common properties or occupy similar cosmic environments, that could provide crucial clues to the underlying physics. If they're truly scattered randomly across space and cosmic time, with no obvious commonality beyond their strangeness, that might suggest multiple distinct phenomena producing superficially similar anomalies, complicating the search for explanation. The discovery has also reignited philosophical debates about the nature of scientific explanation itself. What counts as understanding a phenomenon? Is it sufficient to develop mathematical models that accurately predict observations, even if those models seem bizarre or counterintuitive? Or does understanding require something deeper, an intuitive grasp, a conceptual framework that makes sense not just mathematically, but in terms we can mentally visualize and comprehend? Quantum mechanics has long exemplified this tension. Its mathematical formalism is extraordinarily successful, making predictions confirmed to astonishing precision. Yet its conceptual interpretation remains contentious nearly a century after the theory's development. What does it mean for a particle to be in a superposition of states? What constitutes a measurement that collapses the wave function? How does quantum entanglement connect particles across space in ways that seem to violate locality? Physicists can calculate with quantum mechanics, can use it to design technologies and make predictions, yet many would admit they don't truly understand it in the deeper sense of possessing an intuitive mental model of what's really happening. If Webb's discovery leads to new physics, we may find ourselves in a similar situation, able to describe the phenomena mathematically, able to predict when and where such objects will be observed, yet lacking the intuitive understanding that makes the phenomena feel comprehensible rather than merely describable. For some scientists, this would be entirely acceptable. Science, in this view, is fundamentally about prediction and control, about finding patterns in nature that allow us to anticipate future observations and manipulate physical systems to achieve desired outcomes. Intuitive understanding is a pleasant bonus when achievable, but not essential to the scientific enterprise. Others find this position unsatisfying. They argue that genuine scientific understanding involves more than mathematical description, that it requires conceptual frameworks, allowing us to make sense of phenomena in terms that connect to our existing knowledge and experience. Without such frameworks, they suggest, we haven't truly explained anything, we've merely catalogued patterns without understanding why those patterns exist or what they reveal about reality's underlying nature. These philosophical debates take on practical significance when considering how to proceed with research. If we're content with mathematical description, then the path forward involves developing ever more sophisticated models, fitting parameters to observations, seeking predictive frameworks regardless of their conceptual intelligibility. If we demand deeper understanding, we must also invest in conceptual development, in searching for new ways to think about space, time, matter, and causation that might make currently inexplicable phenomena comprehensible. The emotional impact on researchers working with this data is worth noting. Scientists are human, subject to the same psychological responses as anyone encountering something genuinely beyond their understanding. Several researchers have described feelings of profound disorientation when working with this data, moments when the numbers and images seem to undermine the stability of their worldview. One astronomer described spending hours staring at the spectral data, experiencing a growing sense of alienation from the cosmos she had dedicated her career to studying. Another spoke of dreams where space itself became unstable, positions and distances shifting incomprehensibly, a nightmare reflection of the positional ambiguities in the data. These reactions aren't superstitious or unscientific. They're natural responses to encountering something that challenges fundamental assumptions about reality. Scientists build careers on frameworks of understanding that, in ordinary circumstances, prove reliable and productive. To suddenly encounter data that seems to violate those frameworks generates cognitive dissonance, a clash between what one knows should be true and what the observations appear to show. This dissonance is uncomfortable, sometimes deeply so, but it's also the spark that drives scientific revolution. The discovery has attracted attention far beyond the astronomical community. Philosophers have seized on it as a case study in the limits of empirical knowledge and the relationship between observation and theory. The media has reported on it with varying degrees of accuracy and sensationalism, with headlines ranging from sober discussions of unexplained astronomical phenomena to wild speculation about alien technology or rifts in the fabric of reality. The public response has been fascinated curiosity mixed with a certain anxiety about what it might mean if our universe is stranger than we imagined. Some have drawn parallels to the discovery of pulsars in the late 1960s, when Jocelyn Bell Burnell first detected radio pulses with astonishing regularity from a point in the sky. The signals were so precise, so artificial seeming, that the research team half seriously considered whether they might be receiving communications from an extraterrestrial civilization. They nicknamed the source LGM-1 for Little Green Men. Only after additional pulsars were discovered, after theoretical work explained how rapidly rotating neutron stars could produce such signals, did the astronomical nature of the phenomenon become clear. Perhaps Webb's anomaly will follow a similar trajectory: initial bafflement, followed by theoretical insight, culminating in a natural explanation that expands but doesn't overturn known physics. But there are important differences. Pulsars, however initially mysterious, never violated fundamental physical principles. Their periodicity was surprising, their energy output remarkable, but nothing about them challenged energy conservation, the structure of space-time, or the laws of atomic physics. They were a new phenomenon requiring explanation, but the explanation could be constructed within the existing framework of physical law. Webb's detection appears different in kind, presenting anomalies that seem to require modifications to the framework itself. The question of extraterrestrial technology has inevitably arisen, though most astronomers consider this explanation extremely unlikely. The anomalies, strange as they are, don't bear the hallmarks of artificiality. There's no information content in the energy fluctuations, no apparent functionality or purpose to the observed properties. If an advanced civilization were constructing something capable of producing these effects, we would expect some signatures of design regular geometric patterns, information encoding, evidence of energy being harnessed and directed toward specific ends. The phenomena observed appear more like natural processes operating under unknown conditions than technological artifacts. Moreover, invoking extraterrestrial technology doesn't actually explain anything, it merely displaces the mystery. If the anomalies are products of alien engineering, we still must ask, what physics allows such engineering? How do the aliens accomplish what appears to violate energy conservation? What understanding of space-time permits structures that occupy ambiguous positions? Claiming aliens did it doesn't answer these questions. It just suggests that someone else knows the answers while we remain ignorant. Still, the possibility cannot be entirely dismissed. Our understanding of what constitutes life, intelligence, and technology is necessarily limited by our single example life on Earth: human intelligence, human technology. Perhaps intelligence can take forms we haven't conceived. Perhaps technology operates on principles we haven't discovered. Perhaps the signatures of artificiality we look for reflect anthropocentric bias about what technology should look like. If we encountered something genuinely beyond our comprehension, would we recognize it as designed, or would it appear to us as bizarre natural phenomena? This question connects to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing somewhere in the vast universe and the complete absence of evidence for such civilizations. If intelligent life is common, if even a small fraction of those intelligent species develop technology and expand across their stellar neighborhoods, the galaxy should show abundant evidence of their presence. Yet we see nothing, no artificial radio signals, clearly artificial in origin, no unexplained structures in space, no evidence of large-scale engineering projects that should be visible across interstellar distances. Where is everyone? One resolution to the Fermi paradox suggests that advanced civilizations transcend the physical universe, moving into other dimensions, virtual realities, or states of existence we cannot perceive. Perhaps what we would recognize as technology represents only early-stage development, and sufficiently advanced engineering operates on principles so foreign to our understanding that we can't recognize it as technology at all. Could Webb's anomaly be such an artifact, something engineered but beyond our capacity to recognize as engineered. The speculation leads down rabbit holes of increasingly untestable hypotheses. Without evidence pointing specifically toward artificial origin, the extraterrestrial technology explanation remains an exotic possibility to be kept in mind, but not to be pursued as a primary research direction. The scientific method requires that we exhaust natural explanations before invoking extraordinary ones, and natural explanations, however elusive they currently appear, remain the most productive avenue of investigation. As observations continue and theoretical work intensifies, researchers are developing a list of questions that might help narrow the range of possibilities. Is the object unique, or are there others like it? If others exist, do they share properties suggesting a common origin or similar formation mechanisms? Does the object interact with its environment in observable ways, gravitationally attracting nearby matter, producing particle emissions detectable at other wavelengths, distorting the surrounding space-time in measurable ways? Are there temporal patterns in its behavior beyond the 3.7-hour cycle, longer periodicities, secular evolution over months or years, correlations with external events? Each answered question constrains the theoretical landscape, eliminating some possibilities while supporting others. This is how science proceeds, even when confronting deep mysteries through systematic observation, careful measurement, and rigorous analysis, building up an ever more detailed empirical portrait until the pieces begin to cohere into understanding. The role of Webb itself in this investigation cannot be overstated. Never before have we possessed an instrument with this combination of sensitivity, wavelength coverage, and spatial resolution operating in the infrared spectrum. The telescope's ability to detect faint signals, to analyze spectra in exquisite detail, to monitor objects over extended periods while simultaneously conducting surveys of vast regions of sky, enables investigations impossible with previous technology. If this anomaly had been detected by earlier instruments, we would have far less information about its properties, making the mystery even more intractable. Yet even Webb has limitations. Its infrared focus means certain wavelength ranges remain inaccessible to its instruments. Its position at Lagrange point 2 means it cannot observe objects too close to the Sun in the sky. Its suite of instruments, comprehensive as they are, cannot measure every possible property of distant objects. There are questions about Webb's anomaly that cannot be answered with Webb's data alone, requiring coordination with other observatories across the electromagnetic spectrum and throughout the solar system. Plans are underway to observe the object with X-ray telescopes, searching for high-energy emission that might reveal extreme physical conditions. Radio observations at multiple wavelengths will map any associated structures and search for spectral line emission from molecules or atoms in less exotic states. Gravitational wave detectors, though primarily designed to detect violent cosmic events like merging black holes, will analyze their data streams for any anomalous signals correlated with the optical and infrared variability, checking whether the energy fluctuations might involve gravitational wave emission. Future missions may provide capabilities crucial for understanding this and similar phenomena. The proposed extremely large telescope, with its 40-meter mirror, will offer unprecedented light-gathering power and spatial resolution in the optical and infrared. The Laser Interferometer Space Antenna, a proposed space-based gravitational wave detector, would be sensitive to gravitational waves at frequencies impossible to observe from Earth, potentially detecting signals from exotic cosmic sources. Next-generation radio telescope arrays will map the universe's radio emission with extraordinary sensitivity and angular resolution. These future instruments will continue the investigation long after the initial shock of Webb's discovery has faded, building the comprehensive observational picture necessary for genuine understanding. Science operates on timescales measured in decades and centuries, not months or years. The mysteries that prove most resistant to quick explanation often become the most fruitful areas of research, driving theoretical innovation and technological development across generations. There is something simultaneously humbling and inspiring about confronting the limits of our knowledge so starkly. We have learned so much about the universe over the past few centuries, unraveling its origins in the Big Bang, mapping its large-scale structure, understanding the life cycles of stars, decoding the fundamental forces and particles that comprise reality. It would be easy, with such accomplishments, to imagine that we have nearly completed the puzzle, that only details remain to be filled in. But the universe, it seems, is not nearly finished surprising us. Webb's anomalous detection serves as a reminder that our knowledge, vast as it may seem, remains fragmentary. We are children exploring the edges of an ocean, having waded perhaps ankle-deep into the waves, mistaking the shallow waters near shore for the entirety of the sea. What lies in the depths remains largely unknown, largely unknowable with present methods and frameworks. Yet this realization should not inspire despair, but wonder. We are privileged to live in an era when the universe still presents us with genuine mysteries, when our instruments can detect phenomena that challenge our understanding, when discoveries still lie ahead that will revolutionize our conception of reality. The complete mapping of knowledge would be, in a sense, the end of science, a situation devoutly to be avoided. Better by far to confront mysteries, to struggle with anomalies, to experience the vertigo of encountering something genuinely beyond current comprehension. The search for understanding continues. Researchers pore over data, examining every detail for patterns or correlations that might provide clues. Theorists construct models, exploring whether modifications to known physics or entirely new frameworks might explain the observations. Observers plan additional campaigns to gather more data, to extend monitoring over longer timeframes, to search wider regions of sky for similar objects. The scientific community argues, debates, proposes, and critiques ideas engaged in the messy, contentious, ultimately productive process through which knowledge advances. And somewhere, nearly 1 million miles from Earth, Webb continues its patient vigil. Its golden mirror collects photons that have travelled across billions of light years. Its instruments analyse the light from cosmic sources beyond human imagination. Its data streams back to Earth, carrying information about a universe far stranger and more wonderful than our ancestors ever conceived. Among those data streams are the signals from that anomalous object, still pulsing with its mysterious 3.7-hour rhythm, still occupying its ambiguous position in space, still defying our best attempts at explanation. The story is far from over. In the months and years ahead, new observations will accumulate, new theoretical insights will emerge, and gradually, painstakingly, understanding will begin to crystallize. Perhaps we will discover that the anomaly fits within known physics after all, once all the relevant conditions and contexts are properly understood. Perhaps we will need to modify our theories in specific, limited ways to accommodate these observations. Or perhaps we stand at the threshold of a genuine revolution in our understanding of reality, a transformation as profound as the quantum revolution or the relativistic revolution of the early 20th century. Whatever the resolution, we are living through a moment of genuine scientific excitement witnessing the unfolding of a mystery that may reshape human knowledge. The universe has spoken in a voice we do not yet comprehend, transmitting a message we cannot yet decode. But we are listening, and we are learning, and with patience, rigor, and creativity, we may yet understand what the cosmos is trying to tell us through this strangest of signals from the deep.